mix them, but go for a simple solution. So if I look at something that's going to emit both sulfur dioxide and nitrogen oxides, and I'll have a mean, I'm just going to use the same units for each. Go for fairly simple units. I'll go for parts per million. Parts per million simply means that there's that many molecules of it per million atmospheric molecules. I obviously want the same units for sulfur dioxide. I'm just going to make some assumptions and just try to sort of illustrate the use of it really. Let's assume that we're going for a mean of 8 and a standard deviation of 1. Why not? And we might have less nitrogen oxide, so let's go for a mean of 5 and a standard deviation of 1 again. No, let's go for 1.1. Okay, so I'm looking for the maximum combined value in parts per million. So we're assuming this is emissions that are coming out of the chimney. So we've got a bit of sulfur dioxide coming out and a bit of nitrogen oxide coming out, both of which can contribute towards acidity, acid rain and the like. Now I'm not going to go into the chemistry of it, because actually genuinely, with these getting into the chemistry of it, starts getting a genuine assessment of acidity. It's got to go with something fairly simple, which is a highest value from them both. So, I don't really mind what time scale I'm looking at. So, time 1, time 2, and so on. So, logically, we're just going down a time scale. There's a mean, there's standard deviation. So I want the amount of sulfur dioxides and the amount of nitrogen oxides. Because they can come in a whole variety and then transfer from one to the other, we tend to just call them NOx. I would like that as a capital. So we're looking at using that value. So for the normal distribution, you need to use both the function rand and the function norminv for this. The reason that you need to do that is to get a normalised random variable. You don't want it to be equally likely to find any value, you want it to be most likely to find the value near to the mean. because that's what the valve shape and the normal distribution gives you. So if I use that function for sulfur dioxide, I've got equals norminv, and you don't need to think too hard about it. That's what you want to use for a normal distribution. Norminv, bracket, rand, bracket, mean standard deviation. If you forget what to use, go on to Google and ask it how to tell you how to find a normalized random variable in Excel. And you'll find it quite easily, because that's what I do every time I've forgotten. So I know you can do it. It's easy to find in Google, so when you forget what you've got to do, and the mean is 8, and the standard deviation is 1. End of story. I get a value. So it's given me a random value, which normalised random value that comes off that distribution. Don't forget they keep changing. What I do need to do though is that those values are the ones I want to keep. I don't want every time I copy it down another row, I don't want it to fall down another row. I want it to be genuinely the value that's in D6. So I add $1 before the D and $1 before the 6, and the same with D6. The dollar tells me that that cell is the cell that I want, no other cell. So whenever I copy it this way, that way, it's still going to keep those numbers. Dollar's really important. And then I'm going to do the same for the NOx. If you don't put the rand in, you don't end up with it being random value. Mean, standard deviation, and of course I can just put the dollars in to start with. And genuinely I don't think I want, oh no, it doesn't really matter how much I'm quoting it to at the moment. So that's what I'm randomly getting first time. And remember, it changes every time you do something, because every time Excel does something, it will change the random variable on it. So I'm getting a whole series of numbers that you can see logically come off something, a mean of 8, standard deviation of 1, mean of 5, standard deviation of 1.1. And I can do this for as long as I like. Easily, simply by copying. Just for those of you who aren't familiar with Excel, if you click and get that this cross down the bottom right, hold the left click on the mouse, you can just drag it down as long as you like. So I'll seem to have got to about here. I've got quite a lot of values. So I've done, all I'm doing is repeating the same experiment. The experiment is to get a random value off that one possible thing. And what I'm looking for in the end of this is the total. So I'm looking for the total parts per million. So I'm just going to add those, which I can do like that, or to be honest, I'll probably do just as easily by saying that one plus that one. So I've got a total, and I can copy the total value. So I've now got 100 and odd rows of the total. 206. Doesn't really matter. It's not a, in terms of Monte Carlo, 200 and odd runs is not a lot. Well, let's look at the final outcome. So I've used Monte Carlo on the emissions of sulfur dioxide and on the emissions of nitrogen oxides. They're both acid gases. Bit of a clue in working out whether it's an acid gas is if you take the name and you can then add an acid, it's acidic. So sulfur dioxide, sulfuric acid, nitrous oxide, nitric acids. So we know we've got acids, but this is just an example. So I've got quite a lot of different values, but I can average it. And generally easier to average it up the top, so I don't have to keep running down in order to see what my answer is. So if I go for the average, for the maximum combined value, so I'll put it over here. So I'm going to put the average value of, actually I've got a strong average, of all of these totals. And that's as far as I got. End of bracket. So that's the average of all of those values. The average from E11 right down to E216. So I'll just take an average. Now, I've got a mean of 8 and a mean of 5, so I'd expect the average to come out to 13. So, logically, I don't really need to go through this. I could just work it out analytically. And the advantage of Monte Carlo is that you can use it on things that take a lot more doing to work out analytically. Actually, here it's relatively simple. So I'm expecting a value around 13. So if I keep changing things it's probably going to keep somewhere around about 13. And indeed it does. So it's less accurate than the analytical method, but it's easy. All I've done is set up loads of trials. You can analytically work out what happens when you throw a dice lots of times, or you can just try it. Either of them work, but for quite a lot of instances, the analytical is quite a lot more difficult to work out. So one of the reasons for doing it is on cases where the analytical is more difficult. I'm just trying to use a simple example to give you a bit more of an idea of what it's doing. Any questions on that? Okay, let's see what happens if, just have a quick look down and we'll have a look at the figures. And they all look sort of okay-ish. They don't look too bad. Now let's try changing some of these standard deviations and see how much difference that makes. We were quite close to 13. We're going to up the standard deviation to say 3 and 2. I'm still quite close to 13. It shouldn't actually make a difference to the eventual answer. I'm just putting any old number in here just to change it. But it's coming a bit further away. So I've got a broader spread on both now. I've tried changing standard deviation to a number that's a bit bigger. So I'm getting a broader spread, so I'm not getting as close to 13 every time. Let's try that again. Try happy again. Standard deviation 5 and 3. And again, we're getting a little bit further away. 13.6 is a bit further away. Yeah, absolutely.
When we want to achieve 13, that's the result from the average, right?
Yeah.
And now when we're claiming before negative 1, something out of the structure
what?
Why we're changing vocabulary like the verdict?
Yeah, that's what I'm saying. It's a simple thing to do. This is using a simple example to illustrate how the technique works.
Yeah, why we keep going?
Where?
Why we keep going?
We found 13. What? I'm trying to illustrate how Monte Carlo works. We know 13 is what we want. We've got a value that's fairly close to it. But when you've got a small standard deviation, you're going to keep a lot closer to that. So what I'm trying to illustrate is how many, with a small number of runs, like 200s, we're not going to get the exact answer. If the standard deviation is quite a lot bigger, you're going to be further, you're likely to spend more time further away from the exact answer.
How many times would you recommend it?
Depends what you're doing. Generally, I would sort of until your trigger fingers got tired. 10,000. I don't mind how many you use, to be honest. I wouldn't use less than 1,000. If you're going to do a Monte Carlo, I would suggest that what you're doing is illustrating a method. You're never going to get perfection no matter how far you go. So whatever you do, pick a number, go for it, and then discuss the fact that if you did more, it'd be more accurate. And that answer is going to be the same whatever. But I would suggest that 200 is quite small. 1,000 is beginning to get more into, get more close to it. The other thing I want to look at though is things like that. And indeed that. So what I've done is use Monte Carlo to simulate a perfectly simple sum, but I'll take lots of runs. Because I've got quite high standard deviation now, there's always the possibility a normal distribution goes off to infinity in either direction. So most things don't actually conform to a normal distribution. Most things conform fairly accurately to the middle bit of a normal distribution. People's height, people's weights, they tend to conform reasonably to a normal distribution, but in theory they go to infinity either way. And no matter what sort of a diet you're on, you're not going to go to minus infinity in terms of weight. And no matter how much of a weight bodybuilder you are, you're not going to go infinity the other way. So it's not a totally accurate representation. And once we start getting into a standard deviation that is reasonably high by comparison with the mean, you've got a fair chance of going negative. Now, I'm looking at emissions from this incinerator. If I could achieve that, I'll be quite happy, really. I'm setting stuff up for this incinerator which is reducing the amount of nitrogen oxides. The government will be ecstatic. They're all on there trying to reduce. This is carbon capture in the extreme, except for nitrogen capture. It's not real, sadly. It's simply a mathematical effect. So sadly it's not real, but this would be carbon capture, or at least acid capture. So the question then becomes, what do you do about it? Mostly, you can leave it. It's an obvious idiocy, but within the context, we still end up with about the right answer. So, I would recommend that mostly you leave it. depends a little bit on what you're trying to do Monte Carlo for, and sometimes you need to actually stop it from going negative. So you could stop it from going negative. If I look at that, I could, instead of that, have, let's just have a look at the top one here. So, I've got this equal normings round of that lot and that lot. If I don't want it to go negative, I could go for the maximum value of that and 0. So I've now taken, I've got to find normings, and I've taken the maximum of this and 0. So if this is a positive number, it'll take it. If it's a negative number, it'll take the 0 instead. The arguments for either are not particularly. You could do either, but you need to you need to think about what you're going to do with zeros. Mathematically, you can do either. Mathematically, it's really slightly better to leave it as it is, unless that ends up with nonsense. So it depends quite on the situation that you're modelling. But if I copy this one all the way down, and let's look at the values I've got. You can see now I've got a 0, which is quite unlikely to be a genuine 0, it's probably somewhere negative. And I've got a 0 here, whereas I've got some negatives on that side, so it doesn't change it. So that's an option that you could do that. Well, that really is all there is to Monte Carlo. You just keep taking an example and take another. You keep taking these random numbers and then go for averaging it. The difficulty is in deciding what you're going to do a Monte Carlo with and what values you're going to take. Some of the information is in what you've got. Some of it isn't. Sometimes you might have to make an assumption. If you've got to make an assumption, then it's worth seeing what happens if you change that assumption and how far different it gets. So, maybe this one's going to be 8, maybe it's going to be 8.1. But again, what you've got to set up with the initial data at the top, you can just change it and see what answer you get as a change. It's a model. In some ways, what